Test. Okay.
We're already streaming, so we're set.
Okay. Is the speaker active?
Yes, it is.
Okay.
As a matter of fact.
All right. Good. Where's Kevin?
Kevin will be back soon.
Okay. All right. Do we start on the
100 seconds from now?
100 seconds from now? Okay. All right. Yeah, it just depends upon whose clock is. Oh,
That's very cheap tripod. It's less than $5, $10, $9.
So is mine.
Really?
So is mine. This piece that's more expensive.
I can use this one, simple. So I just clip my iPhone 7
And you just clip it right in
then
there.
it's 4K. Worldwide.
It works.
Live.
Oh, it's great. I do my phone out there too. Like I said. All right. Hey, what time do you think it is?
It is time.
Yeah,
Okay.
Oh, come on.
We can start on time at 30 minutes.
Okay.
120
Anytime
seconds.
you want to start, go.
Yeah. So this clock is kind of off.
Oh, boy.
Oh, just 1 minute. Let me get online.
Yes, we are alive.
Okay, good. In the YouTube. We are live. Yeah, that's good.
Let me try to connect it to the network. Okay.
I bought it when it was Kickstarter. So
It's now public.
Now, they've got a whole bunch more attachments. It's gotten better. But it's look up Beastie Grip. Beastie Grip.
Using Huawei?
No, this is just a Samsung.
Oh, Samsung.
But it fits any size. Any size that you want to go.
I might look at that.
Yeah, it allows you to actually have tripod mounts, a flash mount.
Wow.
You've got better grips on the newer ones. No.
Connected.
You have to get the lenses for that. And I haven't worked out the lenses. With a phone, you have autofocus, which doesn't work with lens. You have to fix the focus and then project the lenses have to project on a surface that the phone can not focus on. And they have a whole process. I went through the whole thing and then started getting into big money. The lenses are big money.
I see. I like simple things.
Okay. Can't get. Let me see. July 4th. Okay. July 4th. July -4th. All right. try it again. Stanford.
Yeah. Now you're definitely 1031. Yeah.
Okay, sorry. Let me get. I need to get it connected. I just need to get connected. Public. Okay.
You probably have to close your browser and open your browser again.
Close the browser and open it again. Oh.
You have to close the browser and then open it and then it says stop.
Okay. Well, let's forget about it.
Well, no, don't forget about it.
Later. Yeah, I think. Okay.
Okay, good morning.
Okay. Good morning. This is Silicon Valley Fourth Interest Group, and I'm Chen Hansen Ting. This morning, the topic is eForth in C, and that's my one of my favorite topics. Okay, hey. Oh boy. All right. Okay, this is just a brief review of my implementations of eForth in C. I started that the first one I did was in 2009, and I did one version 1.0, which has 64 byte codes. And immediately after that, I thought I just do the eForth original implementation, which has only 32 byte code. So it's a much simpler one, but more aligned to the original eForth model. So when I did that, it was just I just learned how to implement Forth in C. So I didn't really expect any use of it. And in 2011, when the Arduino Uno kit came out, I was kind of excited. So I tried to port. I did implementation with a 328 assembler, and I was pretty happy with that. But that system was not compatible with Arduino, because the Arduino IDE, they have the traditional model that you have programs in the flash memory and data in the RAM memory. So when I try to put forth in Arduino, I have to use the flash memory, and I have to write into the flash memory to extend the dictionary. And the Arduino IDE really does not like you to write into the flash memory. And the flash memory, if you want to write into the application memory, you have to write it from the bootloader sector. Okay, so your read-write routine has to be in the boot sector, and then you can write into the application sector. So in order to extend the fourth dictionary, I have to take over the bootloader. And this way, I have the entire memory available for me, and I can read and write into any place. But then I have to throw away the Arduino IDE. Once I have my Forth loaded, you cannot load any Arduino applications. So that's a kind of I don't mind, but people has the Arduino Uno was troubled with that. So I thought, well, I just use conform to the Arduino IDE and just write my forth in the flash memory. And when I extend the dictionary, I just put the extension into the RAM memory. That worked, and I used this, ported my eForth model into this configuration. The only trouble is that after everything is working, I've got only 1.5 kilobytes of RAM memory left for the dictionary. And that doesn't allow you to do any substantial application. And another thing is that the dictionary is in the RAM memory. If you turn off power, your application is gone. But it just shows that, yes, I can put C into the Arduino. I mean, put an eForth in C on the Arduino. It's only it was only a teaser. You can try it. It's compatible with any other Arduino applications. You can try and bring forth up, but you can't do much with it. And last year, I got the ESP8266 kit, and this kit has a lot more memory. It got 150 kilobytes of RAM memory and 4 megabytes of flash. So there's lots of memory available. So hosting a big C program is not a problem. So I ported the eForth into the ESP kit. And the ESP chip, it doesn't give me access to the CPU at all. So there's no assembler. You really cannot do much at the very bottom. So everything you have to, if you want to write anything, C is almost the only way. But since it got lots of memory, if I have this forth loaded, it runs very smoothly in the RAM memory. So I was pretty happy with it, and we used this kit at the Maker Fair, and I think it was a success. Lots of people come by, and we bought 50 sets of this kit, and challenge people that if they can turn the LED on and off remotely through Wi-Fi, then they get a kit. So in the second day, first day we gave out about 40 of them, and the next day, Sunday, at 1 p.m., all the kits were gone. So, so that was pretty good. Yeah, lots of people were successful in getting the Wi-Fi to work and actually get the LED turned on and off. But in Saturday, the first day, the Wi-Fi was just horrible. I don't know how many people are on the net, and many times people get everything done, and when they try to send UDP packet, they just couldn't send the UDP packet over. And say, oh well, if you just get the LED turned on and off through the USB, that's okay. You got a kit. But many people actually did get the Wi-Fi UDP to work and turn the LED on and off successfully through Wi-Fi. But in this month, I was try to write the manual and look at the whole system, review the whole system once more, and found lots of things that can be improved. So I go through the eForth 20, put in new stacks, and move everything onto the Visual Studio. So this is the original eForth. And with the experience on the ESP4th, I put in new stacks and moved the eForth. Original eForth was on GCC in the Sigwin. That was a kind of an awkward environment for PC. So I move everything onto the Visual Studio. And a couple of weeks ago, I looked at the code and really feel very bad about the finite state machine, which sequencing through the instructions. Since I have been using bytecode, and there's no reason why I have to build a multi-stage finite state machine for the simple task just to sequencing through the bytecode. So I changed that, and now I can have a very simple bytecode sequencer to go through the bytecode very quickly. So I want to talk about these two improvements this morning. So these are some of the improvements that I've made in the last month. Moved to Visual Studio 2017. That's actually a very pleasant environment. It supports C++, C#, and .NET, and lots of other things. And the stack was changed to a 256 cell circular buffer. So one of the very hard problems in implement fourth is actually how you handle the stack, and when what do you have to do if the stack happen to overflow or underflow. So putting in the checking, the error checking in your system, and then use interrupt or any other ways to handle the error conditions is generally quite involved, quite difficult. And now I have changed it to 256 cell circular buffer. So I use one byte pointer as my stack pointer, and it just wraps around when it overflows or underflows. So it never overflow, never underflow. And with that, you really don't have to manage the stack. Once you initialize stack, you can just keep on going. If anything happened, any error occurred, who cares? Okay, you just start from where you left off last time and start there. So stack overflow and underflow is not really a very serious problem. Yes?
Does the system give you an indication that there was an underflow or overflow?
No indication, because I don't provide any word to read the stack or examine the stack pointer. So you have no way of knowing what the top of stack or if there's an overflow or underflow condition, because I don't consider them to be errors. Okay. Yes, if it overflows, it underflows, it may overwrite your data, your very old data on the stack, but that would cause problems. But it's not going to. It's not serious enough to cause you to shut down the whole thing. Yeah.
On the stack, there's no method then of of determining that if you've got code running, if you've got some kind of problem, you can't find out what it is. You're overflowing the stack or underflowing it. Is there any flag you can set so that you can say, hey, I had, from wherever I started, I've underflowed or I've crossed this, say, the zero.
Yeah, right.
Because
yeah,
trying to debug a program.
right, exactly. So the facility I provide is to always show you the top 4 elements on the stack. So anytime it's when you hit that return, it says OK. It also dumps the top 4 elements, and that 4 elements I think is enough for you to examine the stack to know where you are. You put the 1, 2, 3, 4 on it, and you know the last one is a 4. Okay, you run your program, and then if the program doesn't change the stack, you should always have 1, 2, 3, 4 on the stack. If you lose the 4, then you know, well, you kind of underflow it. Okay. So this way, I think one of the very significant advantage is that I don't have to manage the stack anymore. Okay, so there are lots of words, lots of commands in the eForth model that manage the stack. You initialize the stack, you look at the stack, you look at the, you want to ask the depth of the stack, the current depth. Yeah, all these things are not necessary anymore. So if I always have this top 4 element visible, I know where I am, and I can deal with the stack. Yes.
So do you miss .s?
Yes, I actually eliminate .s because I have always seen 4 elements.
Okay.
So that's not, I don't need .s anymore because I don't really need to know how deep the stack is. I just have to know what's the top 4 of them.
So do you recycle space, but do you just like not, in your fourth, do you not have to drop elements that are deeper in stack?
Yeah.
It just overrides them when you're done?
Yeah. If you have to override it. If you want to leave anything on it, leave it on, and next year you can pick it up.
This reminds me of that the mill CPU, right? It's like a conveyor belt thing, and it will. So I think it's like almost like a sort of. I guess it's not really the same thing, but it's like a FIFO instead of a stack machine.
Right. Yeah. So in the now we have 256 elements, levels on the stack. That's a huge stack. Okay. So normally you would never you would never be able to wrap around. Okay, unless you are doing recursive programming. Then all bets are off. Okay, but the stack overflow, underflow is not a big problem. You have to know it. You have to know how many things, how deep you need the stack. Okay, and you have to know what you put on it. Okay.
So
Yes.
This one can use Visual Studio 2000.
Yes. It is moved on to the Visual Studio. Yeah. So
Because Microsoft offers it for free now.
Yeah. It's the Visual Studio Community 2017. So you can download them and install that on your. And then several systems I talked this morning are all on the Visual Studio. It's a very, very pleasant system because the debugger is very good. Okay, so you can single step through the C code very conveniently. And I think that the major improvement is the finite state machine is replaced by a bytecode sequencer. I'll show you the code, and the comparison. General clean up. I go through I try to write a manual and a comment on every command. And when I try to comment every command, I would say, do I really need this command? And if I feel I can have any other way of doing it simpler, I would do it simpler. So I think I have cleaned up most of the things that does not have to be there. And I write the new manual for it. Okay. This thing is not okay. All right. Okay, right now the virtual force machine has 67 pseudocode or bytecode. And this is a very nice, very nice separation layer between your virtual machine and the real force. The machine underneath and the force on top of it. So the bytecode basically serves as the insulation between your machine and the force. Okay, now the bytecode sequencer executes forth bytes in sequence. So you just go to the memory and read one byte after the other and execute this bytecode. So in the primitive commands, in the code field, I have bytecode stuffed into the code field. And in a compound command or high-level force command, the parameter field has token lists. So these are very standard direct threaded force model. Okay, so here is how the stack is declared. I declare return stack 256 elements, all initialized to 0. They are long integers, 32-bit long integers. And the data stack is declared similarly. And the R and S are declared as characters. So they are they can point to the 256 level of stack as a circular buffer. And the top of the stack is implemented in another variable as top. So this is the basic definition of the stack. So in the code, you just have to, I have lots of trouble with this stack, and the underflow condition persists even I declare the stack pointer as a byte. In some instructions, like if I do the S and +1 to it, and if I use S +1 to indicate the next element, or S -1 as the prior element. If I didn't tell the compiler this S +1 or S -1 must also be a byte, then it will take it and then make an integer of it, and then the underflow and overflow condition would persist. But if you take care of declare, anytime you change the S or R, you tell the compiler this is still 1 byte value, and then it will do the right thing accordingly. So this is the original implementation of the finite state machine. The finite state machine was I tried, when I first implemented the C, I have thought about it for a long time how to implement the C, and I couldn't get it, couldn't get a clear picture on how to impose my dictionary onto the C compiler. Finally, I say, well, I've done a 32-bit hardware microcontroller, the EP32. It's a 32-bit machine, and I use 5-bit and 6-bit instructions. So I can pack. If I use 5-bit machine instructions, I can pack 6 instructions to a 32-bit word. If I use 6-bit instructions, I can pack 5 of them into a 32-bit word. And that's why I need a finite state machine. So first, I have many phases. In phase 0, I fetch the next word, and then I decode this however many instructions in the instruction in this word, and then I sequence. I decode all the instructions, and in the next phases, I'll execute these instructions in sequence. And then after I finish all the sequence, this jump code will change the clock to 7. And so next time it add 1 to it, and then start to fetch the next instruction. So this was the design of this, the necessity of a finite state machine for the for a machine which has many instructions in a word. But now I have I decided to use bytecode, so I have 4 instructions per word, and this this finite state machine just sequences it through these 4 bytes. But if the machine can read words and byte, I don't need to read the whole word and decode the 4 bytes. I just read the bytes in sequence, okay? And that makes the machine much simpler. And this is the bytecode sequencer, okay? So you just read the next byte. If you can read the instructions in bytes, and here I declare this data. This data is the dictionary array, and I declare the data array as a word array. So they are 4,096 words in the dictionary. But I always also define a pointer C data, and this C data would access this data array in bytes, okay? So this way, I use a P pointing to the dictionary, and fetch the next byte into the bytecode, and increment the P by 1. And then once I get the bytecode, I just go execute it. And then the next time you come back and fetch the next byte. So this bytecode sequencer, it's just like a hardware microprocessor. It just executes, 1 byte at a time and go. So this kind of realized bytecode machine. Any comments? Any problem? Any question? So with this machine, the inner interpreter, it just this next will have to be the last instruction, last bytecode in a bytecode sequence for a primitive command. So at the end of every bytecode sequence, you execute this next, and the next will just and now the data is a word array, and this word array is accessed by IP, but the IP is a byte address. So you need to shift it divided by 4 to get the word address, and then read the data into the P. Because you see, we are scanning a token list, okay? And each token is the code field address of the word you want to execute. So you get the address into the P, and the P will be taken by the byte sequencer to start executing the bytecode there. But I also use a word pointer because the word pointer is pointing to the parameter field. That's 4 bytes after the code field address. You know, it's probably when you jump to the code, the P is still have the pointer pointing to the next byte. So if you add 3 to it, you get the code field, you get the parameter field. So you can do it there, or I just use word pointer, and which is P plus 4, and I always have that there. And if the called command, called instruction is a high level one, and the WP has the starting point of the token list. If I'm calling a constant or a variable, WP points to the data. So it is very convenient there. But if it is a primitive instruction, and it just process bytecode 1 byte at a time, the WP is most likely not useful. But you know, you can find the parameter field either before you jump or after you jump. Okay, but here it is quite convenient here just to provide the parameter field address before you jump. Okay, and then IP would have to be incremented by 4, pointing to the next token list. So the next time next is executed, it will execute the next token. So the address interpreter is actually used to start a list, start a new list, and the exit is to terminate an existing list. So the do list will have to be the first bytecode in a high-level colon definition. And there you push the IP onto the return stack, and then use the WP, which is the parameter field address, and you just put the parameter address into the IP, and you do the next, and you start a new list. Okay, and at the end of every token list, you have to have this exit instruction, and it just restore the IP from the return address, and then jump to the next. So these, the next and do list and exit, these are the inner interpreters, or I call the next inner interpreter and address interpreter as this do list and exit. So here I'm actually trying to draw a picture of the primitive command, but I lost my picture drawing the smart draw program. So I have to just, every primitive command, you have a link field, you have a name field. The name field is a variable length. You have the first length byte and the string, and the string is a null field to word boundary. And then you have bytecode. And this bytecode can be packed as long as necessary, but it has to be ended with a next. So this is the basic structure of the primitive command. But because I was using the EP32 design, the code field is 4 bytes are allocated to the code field automatically. Okay, so you can have one byte code in it up to 4, and if you have more byte code, you can overflow into the parameter field. So in the primitive command, there's actually not this boundary, or the code field can be as long as it's necessary. So you don't, but you can, another way of thinking is that these 4 bytes are for the code field, and the parameter field is still there, but the parameter field can hold more byte code if it is necessary. In the compound command, the same thing, you have the link field, you have the name field, and in the code field, you have this single code byte do list. So you just do that byte, and because I have a parameter field already stored into the W pointer, so I can use parameter field immediately to pack a token list. But the token list has to be terminated by this exit instruction. Any comments? Okay. Liars do benchmark. So how good is it with a C implementation? And so I was just for the fun of it, because you really, the benchmark doesn't make any sense, okay? Because you have a C compiler between you and the machine, and you really don't know what the C compiler is doing to your code. And the different operating systems have different ways of handling things. So you know I'm not an experienced C coder, so I don't I would not claim that my C code is the best, is the shortest and the fastest. So with all this constraint, benchmark doesn't really make any sense. But anyway, I wrote a test routine to do this in hex, so it's doing 1 million empty loops. And I put in another loop so you can do more than 1 million very conveniently. So the eForth 22, that was using the finite state machine. And it doing 4 million cycles per second on my machine. Okay. Another variable is the machine that you're using. It has very different clock speed, and it probably has lots of other things that I don't know. But change the finite state machine to bytecode sequencer. Give me about a 50% improvement on the speed. So I get my ESP-Forth out and see how does that work. ESP-Forth is running, I think, at this chip is running at the 60 megahertz. Okay. So it is way below, the clock speed is way below the PC. And then it's compiled by the Arduino IDE. And it is kind of interesting that it's about more than 10 times slower than the PC. But with all the variables behind them, so it is not surprising. But I was kind of disappointed that it can do less than 1 million cycles per second. So just for the fun of it, I open up the 586 eForth 5.0, 5.02, which is in assembly. And it is in assembly, but it is assembled under Visual Studio. And it's 270 million cycles per second. Okay. I don't know what it means, but that's the take me as a liar, okay? But I think it's interesting. I might, if I have time, I could show you this code. I mean, demonstrate these systems. So let me see. How are we doing with time? Shall we break at 11:30? Yeah. Okay. Okay. So let me just show you some of it. Okay. So eForth. Okay, let me show you the slowest thing. For some reason, this one doesn't compile. Can't show it. It's the slowest one. It used to work at home, but I don't know what happened to it. It compiles all right, but it's done downloading. But the serial terminal doesn't seem to like it. Well, because that's because I'm showing it. Let me just try it. Just get the serial terminal up again. You know, it's still. Oh, I know. Sorry. It is trying to connect to the SVFIG router. Okay. Yeah, it's trying to look for that. Okay, and I forgot to bring the router with me, so it is just keep on waiting for that. And I don't think I have any way of break that process. So let's just forget that. It's the router. Okay, it's this system. It is running the serial port through the UART cable and the UDP communication channel at the same time. So when it boots up, it's looking for it try to sign up on the router, and the router name is SVFIG, and the password is 1234567 It couldn't find it. It's at my home. It's too far away. Sorry about that. Let me see. Of course, I can change this sign, the router, and but I think it's just too much trouble. Okay, this is the Visual Studio, and I have CE420_23 there. So this is the C code, and let me see. You just have to. You see here, there's in the project, it's the CCP file, which is the C++ code, and it has also the stdafx, and this one is the what Microsoft called pre-compiled header. Okay, it tried to pre-compile all most of the headers that the people would use, so that you don't have to you don't have to include them. Okay, but for some reason I still have to have oh no, everything's okay, and I put the dictionary into a header file. So the whole dictionary is compiled by eForth and put into a big data file, and I just call it ROM _23, included as a header file, and it would just construct allocate 4,096 cells of memory and put in the eForth dictionary in it, and then the virtual for basically this C++ program is the virtual force machine, and there I defined all the bytecode. Each bytecode is a C routine, and then I have a big 67 element bytecode table, which points to various C routines, and then the byte sequencer will just go to the memory and read bytes, 1 byte at a time, and through the byte code array, find out the executable C routine and execute them. So this is the basic C++ program. And here you do the rebuild, and it takes us a couple number of seconds. So it will just compile everything, because it is it also uses the header file and then the C++ code, and in a few seconds you to finish and report everything's okay, I hope. Okay, here you have build all, 1 succeed, 0 failure, 0 skipped. So all is well. And now you go to debug and say start debugging. Oh, a minute or so. It takes a lot of time for you to think. But the debugger is very nice, very powerful, very nice. You can set up a breakpoint anywhere, and you can open up data array, and you can monitor the data stack, return stack, and anything that you want to look at. So there, it opens up a console, a Windows console. This is run as a Windows console application. Okay, so you got this little window open up, and if you push, you got this, and the words. Okay, you see all the words there, and I might just well do the test 4 1 0 0 0 0 4 4 next. Okay, so if I do say 10 times of it, 10 million times, it's about 4 seconds for 10. Actually, it's not 10. It's 16 million cycles. 16 million cycles. So it takes about 4 seconds to do that. And that's 4 4 megahertz. Oh well. So this is the EP32, and this one is with the this is with the bytecode sequencer. So it just has 2 steps: fetch next byte, execute next byte, and fetch next byte and execute next byte. So this is very nice. I'm very happy with that. Let me see. So that's this is this guy. And now let me try to open up the my recent projects, recent files. Okay, so this project, I have my this is the eForth in assembly, and so it's 5.3. And this is the I first thought that the 86 eForth was originally compiled under PC-DOS with Mazen, okay? And when I tried to reactivate it, I couldn't find Mazen anywhere, okay? And then digging through, it was still there. Microsoft still have it, and it's hiding behind the C++ compiler, okay? So you just run it as a console application in the C++, but not giving it a C++ file, giving it a .asm file. It will do the same, okay? It doesn't mind. So here you can see this project has only one file, 86 eForth 503.asm, okay? So it's pretty much the same file that I according to the original eForth model. But the eForth model, it was originally in 8086, and then we got the 186, 286, 386, and up to 586. So over there, originally it was a 16-bit implementation. And then it got the change into a 32-bit implementation. Then we have to get through the real mode and the protected mode. Remember these things. And finally, the real mode went away, and everything's becoming linear. Okay, you don't have the segments anymore. So this is going through all this evolution. Evolving into the current 32-bit implementation, which I call the 586 eForth. And the same thing, I think, pretty much do the same thing, rebuild solution, and try to assemble, and success. And then go to the start debugging. Basically, the same thing. The only difference is the speed. Okay. So the implementation, I have tried to align all the eForth implementation to the same model. And remember, you see here, I display top 4 elements. And that's what you need to know, and that's the only thing you have to know. Okay, so if I type 1, 2, 3, 4, and you can see we got 4 elements, and we do a plus, and you got the 7, right? So that's all you need to know. and you just watch, put in something that you are familiar with, and then always watch for that, and you can know if the top of stack change or not. Okay, so that, and you really don't need to know the depth of it. Okay, but here in this implementation, I still have it. So the depth, if I think I still have the depth in this implementation. So I have 3 elements there. Okay, but this implementation has not changed. The stack is still allocated a fixed length out in the memory. If I get time, I probably will change it. But I think I think I need to. Okay, so this is case sensitive. Okay, and let's do the same thing. Test for 100,000 for next. Okay, so I got this thing. If I do the 10 test as I did before, it just comes back right away. So I have to do 100 test, 2 seconds. Okay, then I need to do. Now it start counting, but it's I think it counts up to, I don't know, 40 seconds. But it is 270 megacycles per second, and that's really okay. It came back. Okay. All right. That's all I have for the morning. Okay. Any questions? Any comments? Thank you very much. Yes.
Hey, do you remember when I wrote that fourth dictionary for you in C?
Yes, I lost it.
I'm gonna give that to you.
Yeah, give it to me again.
Yes.
Yeah, I remember you told me that you can do the dictionary, and you gave me some code.
Yes.
You gave me code, but I lost the code.
Yeah, because see, when you have the tables, you have just a bunch of hex numbers.
Mm-hmm.
It's like,
Yeah, that's right. That's right.
Yes,
Uh-huh.
I've got it somewhere on this computer.
Yeah, if you can find it, give it to me, and maybe maybe I can. I just wanted to be able to construct this dictionary in C code. Yeah.
Yes, and this is in C code, definitely in C.
But when you gave me your sample, it's beyond my head. Yeah, that's right. Right. It drove me crazy. Okay.
Yes, it did. Yes.
Okay. Yeah, but you see, when we started the eForth and all these things, I knew at the time, 1990s, there are several C implementations of Forth. And then the most notable one is the Baden's this Forth. And then Mitch Bradley has the Forth Max, right? And these 2 systems were written in C. And Baden gave me this Forth, the whole source code. I couldn't read it, okay, because and I couldn't use it for compile because he used a M4 macro interpreter. He used an M4 to massage the full source code so that he can construct the dictionary, and it's yeah. It's I couldn't find the M4, and I couldn't do anything with it. But I think the Mitch Bradley called his forces, and he used a wrapper, and that was a mystery. Okay, and here's a big makefile. I couldn't get through 3 lines of it. Okay, so basically I gave up. You have to spend my life learning C and learning Unix to do anything. Oh, but I think the nice thing about this eForth implementation is that the dictionary is a separate project. Okay, any way you can do it. Just get the dictionary array and move it into the virtual force machine in C. And it work if you provide the virtual force machine underneath, and you have this big array out there, and this virtual force machine, the bytecode is go into the dictionary, pick up one place where the bytecodes are, and just go sequencing through it, and that's all you need. Okay. Any comments? Okay, I think it's lunchtime. All right. Thank you very much. Yeah.
Wanted to mention that the fabulous West Coast Antique Computer Festival is coming up. I have vintage computer. Thank you. IQ test failure again. Brain is shut down for the weekend. Sorry. Where was I? Oh yeah. I have a few $5 off admissions coupons for those of you that are interested. See me at lunch or when we get back after lunch.
Where is the location?
Down at the Computer History Museum of Doom.
Okay. Next weekend.
And we are off to lunch now. See you in the afternoon.